Good morning, good afternoon, good evening, wherever you are. This is Nick Chase from Morantis, and I would like to welcome you to our SDN Mini-Bootcamp. Okay, so let me introduce you to our presenter for today. We are here speaking to Grzegorz Pavelski. Did I get it?
Yes, correctly.
Okay, thank you. All right. So Grzegorz is a senior technical instructor here at Morantis. He's got lots of experience as a systems engineer. He's worked for IBM and AT&T and Nokia, and he is a specialist in IP networking, IT security, and all things networking. So we are very pleased to have him here today to kind of give us this boot camp on SDN. Thank you so much, Grzegorz.
Thank you.
Okay. All right. So let's before we start, let's do a little bit of housekeeping. If you notice on the right-hand side of your screen, you will see a small, you'll see some sort of box there. There is a way for you to go ahead and ask us questions. We do want your questions, so please go ahead and submit them. We will gather them. We will gather them together throughout the course of the webinar, and then at the end we will take questions. So please go ahead and submit those. We will also be recording this. Broadcast is being recorded, and we will provide it. You will be able to download it. You will be able to get the slides and so on afterwards. So please go ahead and enjoy that. So now let's talk about what it is we are actually going to talk about. So if we can take a look at the agenda, we're going to cover 4 main topics today. We're going to talk about traditional networking so that you have kind of a basis of what's going on. We'll talk about what software-defined networking is, and then we're going to sort of dive deep into some of the protocols. We'll talk about how SDN protocols themselves work. We'll talk about OpenFlow, Open vSwitch, and Open Virtual Network, and then we'll put it into context into how all of this applies in cloud data centers. Now, I do want to take one more moment to talk about what you're going to understand when you're done here. We don't usually do this on these webinars, but this is a very dense topic, and so I want you to understand. So at the end of this webinar, you are going to have some familiarity with some topics. So you're going to understand the very basics of traditional networking. When it comes to SDN, what are the things you need to know? You will understand what SDN is and why that's important, and the basics of it. You will also understand how these protocols work. What do they do, and how do they do it? And you'll be able to kind of relate that to your own experience, both in what you have now, and if you're considering building a cloud data center, you will understand how that all relates. Now, let me just point something out here. This is a topic that we actually have a couple of classes on this. Some of our classes are 2 days long, so we're doing a very condensed look at this topic. So we're going to cover as much as we can to kind of give you something self-contained that you can walk away with and use. But there's additional things that we won't get to, but you can always take the class later if you like. Okay, so moving right along, I am going to turn this over to Grzegorz so that we can talk about traditional networking. So tell us, what do we need to know to kind of get started on this topic?
Okay. Hello, good morning, good evening, or good afternoon. So we have to start from some basis, which is a traditional networking. So this is how very traditional networking looks like, but we want to be more focused on packet-based networking, not circuit-based networking. So we have to cover just a few basics. I'm pretty sure that most of the people here understand already understand what MAC address is, what layer 2, layer 3, etc. Are, but let's start from basic. So this is a simple local network. The central point here on that local network is a Ethernet switch, bridge, whatever you call it. It basically means the same. And the role of this network device called Ethernet switch is to, as its name says, switch frames between different endpoints, different computers. So Ethernet switch is a layer 2 device, so it uses so-called MAC addresses, Ethernet addresses. They are represented using this hexadecimal notation. But computers and applications running on those computers, they don't actually communicate directly using Ethernet addresses. They communicate directly using IP addresses, or even better, canonical name, which represent those IP addresses. So it's layer 2. Sorry, it's layer 3. So on top of layer 2, we have layer 3, and the most popular layer 3 protocol is, of course, IP protocol. And IP addresses, because these are different addresses, this is the different addressing schema than Ethernet, of course. It's represented using decimal, 8 octet, 4 octet address. So this is IP version 4. We also have IP version 6, but let's focus on the simpler case, IPv4. Okay, so we have addressing here in layer 2, we have addressing here in layer 3. So what you have to understand that those addresses, Ethernet addresses, they are only meaningful locally. They are only used locally on that particular switch, on that particular local network. When IP addresses, they can have a global meaning, so it means that you can address any computer. If you use a so-called public IP address, you can address any computer on the planet. So how switching is performed by this Ethernet switch? It builds dynamically so-called MAC table. So this MAC table has 2 columns. The first column is destination MAC address. The second column is destination port. And so when it starts, this table is simply empty. So when a frame comes, it has no idea to which port it should be sent. That's why it is sent on all the ports except for the one it came from. So we call this process flooding. And then when the frame comes back, it looks at the source MAC address, and based on that information, it adds dynamically a new entry to its MAC table. But then, as I said, we use IP addresses. We don't use MAC addresses directly. That's why we need a second table called routing table, and this routing table will be present on all the endpoints, all the computers connected to that network. Also, router. We don't have a router presented here, but we could also have a so-called default gateway router to provide interconnectivity to other so-called subnet, IP subnets. IP network is called the subnet. So we have routing table and forwarding table. I'm going to cover what is the difference between a routing and forwarding table in a minute. And we also need the third table here. It's called ARP table. So ARP table is actually to map IP address. So for example, this IP address here, 1.2.3.4 into MAC address. So when this computer, application A, wants to communicate with application C on host 3, it will need to resolve IP address it knows into MAC address. And we have a special protocol for that. It's called ARP protocol. So the role of ARP protocol is to broadcast a message who has IP address 1.2.3.4, and then the computer which has that IP address replies with a response. So these are the basics of traditional networking. Of course, IP networks are more complex than just more complex than example we presented. They can have many subnets interconnected with the routers, layer 3 devices. We have also some special protocols to exchange routing information. So one of the most popular protocols to exchange routing information on a single network, so-called single autonomous system, the system which is under administration of one person or one group, is called OSPF. And then we have the second protocol called BGP, which is designed to exchange information across autonomous systems. So when you have two networks under two different administrations, then you can use BGP to exchange routing information, to exchange information about subnets which are reachable on your network or other people's networks.
So this is for a single organization that has multiple networks.
BGP actually can be used for this kind of use case when you have many networks on one organization. But it's also the best protocol when you have two parties, you have two organizations, different organizations, and they want to exchange routing information. So BGP is designed also to serve as a routing protocol across different autonomous systems.
Got it. Okay.
So just to sum up, in traditional networks, network traffic is in packet-based networking. Network traffic is split into so-called packets. Each packet has a header, which is typically source and destination address plus some other information. And this header is treated as a kind of instructions for all the interim devices on the path to the destination, just to execute some actions with that packet, which is basically the basic action is to send it to the right path to reach the destination. What is also important to understand that in traditional networking, every device is configured independently. So it's typically performed with a command line. So you log into that device, you configure routing, you add interfaces, and then it starts running, but it happens independently. We can also use extensions to packet headers to allow encapsulation of one packet into another packet. We have so-called overlay protocols like GRE, VXLAN, and so on. So it's also possible to tunnel one packet inside another packet. So this is traditional networking. So this is how a simple traditional network can look like. So we have three routers here. They are interconnected. Then we have some computers connected to those routers. And when one computer wants to send a traffic to another computer, it sends this traffic to the closest routers it is connected to, and then this router decides based on its routing and forwarding table on which interface this packet should be forwarded, and it just follows the same processing on the whole path. So that's a traditional network. Each of those routers is configured independently. So let's see some details. So this is a traditional router. It has a data path. Sometimes we call it forwarding data path. Data plane. Sometimes we call it forwarding or data path. It has interfaces connected. and it also has a control plane. So control plane is a process which computes, which collects routing information and computes forwarding routes, forwarding information, which is pushed back from control plane to forwarding plane. Sometimes, to simplify, we say routing forwarding, and we actually mean it's one and the same, but technically routing is a control plane and forwarding is a data path. It's a data plane. So the role of control plane routing is to exchange routing information with other routers running on the same network. And it uses routing protocols we already discussed. It can use OSPF, BGP, and so on. There are some other routing protocols too. So this is a process which exchanges routing information, and based on on collected information, it computes routes. And then when those routes are computed, they are pushed to forwarding. They are pushed to a data plane, data path, and they are installed. So they get installed from routing table in control plane into forwarding table in data plane. So once we have those routes installed in forwarding, then router can start performing packet forwarding. So if there is packet coming on ETH3, it will just look up its forwarding table based on destination IP address contained in the packet's header, and in this example, that route just points to next hop on ETH2 or ETH1, sorry. So this is how packet forwarding looks like. And this process of routing and forwarding is independent on each router on the network. We also have it's also sometimes simplified, and we say control plane and management plane is the same. But just to give you more clarity, just we will divide control plane into control plane and management plane. So what is control plane? Once again, it's a fast control loop driven by routing protocols like OSPF or BGP. When management plane, it's a slow control loop driven by humans, by administrators. And this management plane is typically controlled with a command line interface over Telnet or SSH. So administrator simply connects to that management plane over Telnet or SSH protocol, and they execute, or even serial console sometimes, and they so it can be Telnet, SSH, serial console, and they execute command line interface commands like, for example, what they could do. They could enable, disable interfaces. They could enable, disable routing protocols globally or routing protocols on particular interfaces. They could also add and remove static routes if they want to override decisions made by routing protocols. They can also add, remove static routes. So in this example, administrator decided to shut down ETH2, so he or she connects over SSH to management plane, and they run a command to disable ETH2 interface. So this is how traditional router on a traditional network will look like. So what are limitations of traditional networking? So manual configuration of devices, it does not satisfy cloud agility requirements. There is no single view or control point of networking policies configuration. there are many protocols to know, so you have to know all the protocols you want to use, OSPF, BGP, because they have different settings, different logic. Another thing, there is no actually standardized management when you use, let's say, a router from or device switch from Juniper. There will be a different command. There will be a different command line syntaxes than, for example, on Cisco. You can easily create many errors due to conflicting configurations. So on, for example, on one router you can configure OSPF timer to be 10 seconds, and on the other network device you can configure the timer to be 3 seconds, and the network will be flapping, the network will be unstable. So that's another problem. Then configurations are detached from business requirements, so you have to translate business requirements into configurations every time for every device from every vendor. There is no direct translation from business requirements. So what do you want to have? What do you want to achieve? It's detached from how you have to configure that. Then localized control plane, so that the routing process is running independently on each router. It also leads to inefficient data plane. It also leads to a convergency problem. Convergency can be much slower, so inefficient data plane convergency problems. So these are all limitations of traditional networks.
So it's no surprise that we're in a situation where we're looking for something better.
Yeah, of course. So people started looking for something better, especially academics and large companies like Google or Facebook. They started looking for something better, easier, and providing agility, providing direct mapping from business requirements, something which can be easily automated, managed, troubleshooted, maintained, and so on. And we have SDN. So SDN, it's once again, it's software-defined networking. So I'm going to try to explain why it is called software-defined and how it is different from traditional networking. So the idea is very simple. We just take most of the management and control plane and we move it into logically centralized SDN controller. It's important to understand that it's logically centralized. It doesn't have to be physically centralized. What is centralized? It's logic. So we take that control plane, so routes are not computed anymore here on a device. And also management is not performed independently on each device. It's just performed on SDN controller, and of course we still need some thin agents. So for example, a controller will compute a route here and push it to agent, and agent will just execute it, will just push it to forwarding datapath, data plane, whatever you call it. The same with management. So we move a brain from a networking device and we move it to a logically centralized SDN controller. So we can say that we decouple control plane from data plane by moving this control plane into a separate logical entity called SDN controller.
Okay.
Of course, yes. Of course, we need a special protocol to communicate information from control plane on SDN controller and agent on device. So those protocols, there are many protocols to provide it, and they have a generic name. It's called SouthBound protocols. So what kind of SouthBound protocols we have? We have OpenFlow, We have OVSDB. So OpenFlow, it's a protocol to push forwarding information from SDN controller to a network device. OVSDB is small, so it replaces this OpenFlow, replaces a control plane running on a device. So it's like a remote hand of a controller to invoke forwarding related actions on a networking device. And then we have OVSDB, which is for management plane. So a controller can remotely shut down interfaces and perform any action it wants on a network device remotely. Of course, SDN controller, it needs some logic program. So we have to program our network state. An application and a software which programs this and controls this network state is called SDN application. So SDN application can be embedded just like in this case, so it can just use internal API to communicate with control plane agents, management plane agents. So SDN application, once again, it contains all the business logic to drive our network state. So now it's not independently driven by each router, it's driven globally from logical SDN controller and software which implements that logic, that business logic to drive network state is called SDN application. This SDN application, it doesn't have to be embedded. It doesn't have to run inside, the software doesn't have to run inside SDN controller. It can also run externally, but then we need one more protocol. It's called NorthBound protocol, and NorthBound protocol is the one which can be used by SDN application to talk to SDN controller to drive network state controlled by that controller. Unfortunately, those NorthBound protocols are not standardized because actually it would be really difficult to standardize all the logic, because here with this kind of solution, the network logic can be completely customized, can be completely it can be almost anything you want. So it's not standardized. Frequently, those NorthBound protocols are based on REST. They are RESTful. They are run on top of HTTP, but not always. So once again, the protocol between external SDN application and SDN controller is called NorthBound. You can visualize it easily because this is north, this is south. So this one we call northbound, this one we call southbound.
Okay, even though the northbound arrow is pointing southbound, but we'll so just keep in mind it's
it doesn't matter because it's actually okay. It's a little bit simplified because the information can be exchanged in both directions. So it's more to represent logic. That it's more to represent this arrow is more to represent that network business logic to drive network state. It comes from SDN application and it's pushed to SDN controller, and SDN controller push it to agent, and agent reconfigures a data path to be in line with our business logic.
Right. Okay.
So the whole chain, it basically translates what do you want to get into configuration enforced on network devices. Okay. So what kind of SDN applications we could have? One of the SDN application we could have is a compute cloud. So compute cloud, for example, OpenStack, it needs to create logical entities. It needs to create logical ports, logical networks, logical routers. logical traffic policies between logical networks. And so we can actually get an OpenStack connected into SDN controller. So OpenStack will drive our network state. So OpenStack can become SDN application which drives your network state. So OpenStack, it just calls SDN controller over NorthBound interface with a request. Okay, please get me a logical port. Please give me a logical network, and then SDN controller translated into low level, and it pushes forwarding configuration into forwarding path through control plane engine. It also pushes network device configuration through a management plane agent, and your network is magically configured.
So in this
and
case,
as well. Mm-hmm.
so in this case, it's Neutron that would be the SDN application, correct?
Yeah. So Neutron is the one which would be a brain application, which would drive business logic to reconfigure and maintain your network.
And then we might have, say, Open Contrail or something like that as the SDN controller.
Yes, of course, you have many options. Okay, this is what we are discussing right now is generic. Okay, it's just an idea.
Right. No. Okay, I'm just trying to hook it into something concrete. Got it.
Yeah.
Okay.
Yeah. As you said, we have Open Contrail, we have Open Daylight, we have Floodlight, we have Cisco ACI, we have Nuage from Nokia, and so on and so on. There are so many implementations, but they follow more or less the same generic idea. Okay, just to sum up, this is again our traditional network from the previous example transformed into SDN network. So this is a very basic example. So what we achieved is actually the same. We can just send IP packet from one device to another, from one server to another. But now we did not configure that manually. We just have SDN application which sent its business logic requirements to SDN controller. SDN controller translated that into forwarding information and network device configuration, and it configured all the devices and all the forwarding paths just to let a server on the right, on the left, to communicate with server on the right. So SDN full picture once again. So sometimes we call those SDN capable network devices, we call them white boxes because they are white, they don't have any logic. All the logic is driven from controller, and business requirements are sent from application, and we have a traffic forwarded through those white boxes across our network. So what are benefits of separate control plane? So we have all control logically in one. I'm going to repeat that it's just logical. It doesn't have to be centralized physically. So it can be still distributed physically, but it's logically one entity, which we call controller. So all control is from a single place: SDN controller, SDN application. All the policies, configurations are centralized, so there shouldn't be conflict anymore. There shouldn't be misconfiguration anymore. Data plane forwarding can be very dumb. All logic is performed by controller. So data plane, it just enforces decisions made by a controller, and controller makes decisions based on input from application. So we can perform very quick deployment of very complex topologies because everything can be automated. We can also have event-based reconfiguration. It becomes possible, for example, when there is a failure, your network, your controller can react to that failure to reconfigure your network properly, to reroute traffic across failed places, and so on. So that logic can be pre-configured in advance. That logic can be computed dynamically. There are different strategies to achieve it. So these are basic. And of course, when your control plane is decoupled from your data plane, it's much easier to perform upgrades, because when you upgrade your control plane, it should not affect your data plane, so maintenance becomes easier as well. So all the aspects like planning, deployment, maintenance, troubleshooting becomes much easier with SDN. Of course, with a properly designed SDN.
Of course.
Just to sum up the architecture, we have okay, from the top we have orchestration, we have applications. Applications, they talk over NorthBound interface to controller. Then we have we can have different applications: OpenStack, Kubernetes, other SDN custom SDN applications. So they all talk over NBI. NorthBound interface to SDN controller. We have SDN controller, as you already mentioned, Contrail, ONOS, Open Daylight. There are many options to use. Then those controllers, they talk to data plane, to network devices over SouthBound interfaces and protocols like XMPP used by Contrail, then OpenFlow used by ONOS and ODL, OpFlex used by Cisco, then netconf, OVSDB, P4, and so on and so on. There are so many options for SBI. And then data plane, it needs to, of course, it needs to be able to talk over a protocol used by a given SDN controller. It can be Contrail vRouter, Open vSwitch, Cisco ACI. They can be software or hardware switches, routers.
Excellent, thank you. All right, so that gives us kind of a general idea of what SDN is and how it works and all that. Now, we are running a few minutes behind, but I really would like for you to give us at least a quicker overview of at least one southbound SDN protocol. You were going to talk about OpenFlow.
Okay, so we are going to talk about OpenFlow as an example of southbound protocol. It was started in 2008. I think, as far as I remember, it comes from Stanford University. It was created as an academic. It started as an academic idea, which turned into industrial standard. Last specification is 1.5.1 issued in March 2015. It's the most well-known southbound protocol. It's been standardized. It's also very popular. So what OpenFlow does, it abstracts a data path into logical entities like flow tables and flow rules. So data path, data plane becomes abstracted with OpenFlow protocol, and controller can enforce this data path configuration over OpenFlow protocol. So in this example, we have this OpenFlow switch connected to two controllers, and they put all the tables and rules. They configure, they enforce tables and rules on that device, which abstracts our data path, so which abstracts the way our packets will be processed by this network device. And of course, we have ingress and output ports connected. So this is how it is abstracted. We have tables, and each table consists of so-called flows. So flows are actually, they look like ACL rules. So they are more like ACL, access control list rules with matching fields. There can be exact match or a wildcard for a given field. And then when packet is matched they are of course in order. So those rules, those flows, they are evaluated in order. And when we match some rule, then we execute action, what to do with that packet. There can be different actions, like, for example, inserting that packet for further processing in next table, sending on the output interface, or sending that packet for further evaluation, for further classification to an SDN controller. It can be action related to modifying content of a packet, and so on. So once again, we have tables, we have rules. When rule is matched for a given packet, then action is executed. What happens when connection to controller is lost? There are options described in the standard. So in 1.0, there is an emergency mode. In emergency mode, only emergency flow table will be used. Starting from 1.1, there are two other choices. Fail secure mode is just to continue as it is with the existing flows, but without sending packets to a controller, of course, because connection is lost. Or fail standalone mode is, for example, to work as a legacy Ethernet switch, as a legacy flooding and learning Ethernet switch bridge, as we described in traditional networking. What are OpenFlow limitations? There is no easy way to introduce new protocols, new headers, because it's standardized. So you have to apply your own extensions for that. So there is no, let's say, out of the shelf way to do it. Then rules are not that flexible because they follow access control list schema. OpenFlow doesn't cover generation of packets, so you need a controller to do it. If you want to generate packet, for example, some ARP request to resolve MAC to IP to MAC address, then you need a controller to do it, to inject packet for you. But OpenFlow standard supports injecting and packet generation by controller. This is how the most popular implementation of OpenFlow switch looks like. It's called OpenVSwitch, and OVS in short. This is a software virtual switch which is supposed to run typically on a compute node where you have virtual machines running. So virtual machines will connect to that virtual switch over so-called tap interfaces, and this switch will be also connected on an uplink physical interface to send traffic to network fabric. So it's designed to be as efficient as possible for packet processing and forwarding. It extensively uses internal hashing because OpenFlow classification is quite expensive from performance point of view. So we typically classify the first packet, and then we install in a cache. We install processing what should be processing outcome if a similar packet comes. So the following packets, subsequent packets, they are not sent for a full classification. They just take a result from cache, and then action on that packet is executed without full classification. OVS is, of course, designed to be connected, to be controlled by SDN Controller. So SDN Controller, to be able to control OVS switch, it needs to support OpenFlow and OVS-DB protocols as southbound interfaces.
So, quick question. So, is OVS, so OVS is an implementation of OpenFlow, or it does other things and it supports it?
Exactly, it's an implementation of OpenFlow plus a little bit more. But
Got
briefly,
it. Thank you.
Okay, so just to make to create a full networking system, it's not enough to have just OpenFlow switch. We also need an OpenFlow controller and all the infrastructure around the SDN controller. So one of the most popular SDN implementations is OVN. It's sometimes people call it OVN. Pronounce it OVN. It's Open Virtual Network. It's created by the same community as Open vSwitch, so it's supposed to be a complementary implementation of SDN controller and all the stuff needed for SDN controller as a complementary to OVS itself. So OVN plus OVS, they create a full SDN ecosystem to be used, for example, by a compute cloud, by OpenStack, other private clouds too.
Okay. So what does this mean for us in the real world?
Yeah. So that takes us to what SDN can do for us in cloud data centers. So what network should provide in the cloud for the cloud? Okay, we need layer 2 VM to VM connectivity because we want our applications to be able to talk, running on different VMs to be able to talk to each other. We also need layer 2 VM to BMS. BMS means bare metal servers. So we also need VMs to be able to communicate with bare metal servers if it is required. Then we need layer 3 VM to VM connectivity. Either intra or inter-network subnet. So when VM wants to talk to a VM running on the same subnet, or VM wants to talk to a VM running on a different subnet. So we need both use cases. Then we need our VM to communicate to external networks. For example, internet. If our VM wants to expose some service to computers running on the internet, which is a typical use case, it also might require nothing, because typically addresses, at least IPv4 addresses you are going to use inside your cloud, will be private, and they will be not routable on the internet, so we need translation from private to public. So we also need nothing. Then we need, at the same time, we need tenant and a network separation. We don't want a traffic leaking from one network to another when it is not configured so by or designed so by policy. So we need tenant network separation. Then we need independent IP address management. Because you are going to have many tenants on one cloud, and they can use overlapping IP addresses. So we need independent IP address management to handle, for example, overlapping IP ranges Then we also need some security-related features like traffic stateful filtering to protect virtual machine from unwanted traffic. So this is what cloud typically wants to do. It wants to protect virtual machines from unwanted traffic, and that is provided by traffic stateful filtering. So it means it's stateful because we just want to block, for example, one direction. At the same, we want to allow VM to initiate any connections it wants. Then service chaining could be also requested. So service chaining is sending traffic through a chain of virtual machines. So it's kind of policy-based routing. So we can have a VM which serves as a deep packet inspection. Then intrusion protection system or so on. We want to send our traffic through a chain of our VMs with those functions, and it's called policy-based routing. So these are high-level requirements, but at the same time, we want to reduce broadcast domains and traffic flooding. Because traffic flooding it takes our bandwidth. We want our virtual machines to be able to move around your cloud without changing IP address and default gateway. We call it VM mobility. So it means that you can restart your VM on any other compute node without need to change IP address or default gateway, or even you can move this VM in live. Then traffic, both intra subnet and inter-subnet traffic should be optimally forwarded. So without so-called hairpinning, tromboning. So we want optimal forwarding. Then all the links. All the physical links, they should be efficiently utilized. So we don't want some links to be underutilized and some links to be overutilized, and possibly would like to separate mice and elephant traffic. We want to avoid congestion, and I want a pony.
Don't we all? Okay, so I love it. Okay, so if we can try and wrap up, because we've got about 7 minutes left, and we want to try and take a few questions.
Okay.
So give us the really quick version.
Yeah. Okay. So with traditional networking, it's hard to achieve because, for example, when you use layer 2 networking, then you have VM mobility, but you have flooding. Then when you start using L3 alone, then you will not have flooding, but you will not have mobility. So the solution here is to use SDN, especially a version of SDN called overlay SDN. So in overlay SDN, we enforce packet processing and path selection at virtual machine endpoints. It means we enforce it on compute nodes which run virtual switches. So SDN is just controlling virtual switches and compute nodes, and then traffic is just tunneled. It's encapsulated into GRE or VXLAN, and it goes through the rest of the network tunnel. So regular SDN, it enforces packet processing on all the at every point of network. Overlay just on virtual switches on compute nodes, and then it's tunneled through your physical fabric.
Excellent. Thank you.
From my side.
All right. Awesome. Thank you so much. So before we move into the Q&A, just really quickly, I want to kind of introduce everybody. We do have a whole class on this, SDN 100. It's 2 days. So if you can imagine how much information you just got in the last, 50 minutes, how much you will get in 2 days. It does include labs. You see the information here, including the pricing. The first class is going to be May 15th. You do not have to be present. We do have virtual classes, and there will be a special price of $1,000 as opposed to $19.95, so that's like half off. Also, if you are here at this webinar, if you can go to the next slide, please. you can get 15% off any of our trainings. So go ahead and grab that coupon code, and you go to training.mirantis.com and you can do that. Now we do have time for a few questions here. So if you haven't submitted them, go ahead and submit them now, and we'll answer them. The ones we don't get to now, we will get to in a blog post after all of this. So let me just answer really quickly. Is SDN 100 for a specific audience? I believe that it's for network architects, engineers, administrators, technical managers, product managers, sales engineers, those kinds of people. Prerequisites, there are no particular prerequisites, but you probably want to be familiar with the Linux command line and the basics of TCP/IP and so on. Okay, let's see. Can we still use traditional routing protocols with SDN? Give us a quick fire answer.
Yeah, it's possible to use. You can still use traditional routing protocol, but then processing will typically of this routing and computing routes will happen on controller. So all the logic will happen on SDN controller, but you can still run traditional routing protocols.
Got it. Okay. Can you use SDN controller from vendor X and network device from vendor Y?
Yes, as long as you speak the same, they are able to speak the same protocols. You can use controller from vendor X and device from vendor Y. It's possible, but they need to speak the common SouthBound protocols.
Got it. How can I install and run an SDN testing environment on my laptop?
There are many options for that. The most popular are the most popular option is to use so-called Mininet. So Mininet can simulate OpenFlow switches, full network of OpenFlow switches, and you can start playing with any topology you want, and just on your laptop.
That's pretty awesome, and we'll make sure to get a link to that in the blog post. All right, we're going to take one more, and then we're going to have to start to wrap up. Can OVN work with other private clouds or just OpenStack?
No, OVN can work with any cloud which has a driver to speak to OVN. So in theory, it can be integrated with any compute cloud you want, but you need that cloud need a driver to be able to speak over NorthBound interface to OVN.
Okay. Let's see, one more. Blah, 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 blah. Which programming languages can I use to write my own SDN applications?
It's okay. It's completely agnostic to languages. Of course, when you run your application embedded, then it needs to be able to speak to a programmatic API provided by this SDN controller. But if you run it externally, what you need is to translate it into NorthBound interface. So it's completely agnostic to programming languages. It can use anything you want.
All right. Tell us what the difference between an overlay and an underlay is, and then we're going to say goodbye.
I think I just partly covered that. So overlay is a network which consists of tunnels.
Okay.
And the underlay is a physical network below that overlay. So, for example, it could be TRE tunnels, VXLAN tunnels, array encapsulations are also possible. We call it overlay. So all the package which goes through a tunnels, we call it overlay. Then what is under those tunnels, we call it underlay.
Excellent. All right. Well, that's it. So we are out of time. We will answer the rest in the blog post. I want to thank our featured speaker here, Grzegorz Pavelski. And I also want to thank Michelle Yakura, as always, for being our rock behind the scenes. And I want to thank all of you for spending your time here with us this morning / afternoon / evening. Thank you all very much, and we will see you next time. You will be able to go ahead and get the slides. You'll get that in an email. And please don't forget, you've got this code here. You can go ahead and register for the class. Thank you all so much. Have a wonderful day.